So we are dealing with the fifth problem in this series, and the problem number is 1.123. The problem is stating two bars of masses m1 and m2 are connected by a non-deformed light spring rest on a horizontal plane. The coefficient of friction between the bars and the surface is equal to mu. What minimum constant force has to be applied in the horizontal direction to the bar of mass m1 in order to shift the other bar? So if we draw a simple diagram to explain this arrangement, so this is the horizontal surface, and on this horizontal surface two blocks are placed connected by a spring of unstretched length having spring constant K, and the two blocks involved, they have mass m1 and m2. So this one is m2, this one is m1. Let us take spring constant as K. Now a horizontal force F is applied on the block m1, and if I again reread the question, so the question is stating two bars of masses m1 and m2, they are connected by non-deformed light spring, and there is a coefficient of friction. So if there is a coefficient of friction, so the first step that we involve is that we calculate the friction at the contact surface of both the block. So to calculate frictional force, we need to calculate the normal reaction force. N2 equals m2g. Frictional force F2 equals mu m2g. Over here N1 equals m1g. Frictional force F1 equals mu m1g. Now the question is asking what minimum constant force has to be applied in the horizontal direction to the bar of mass m1 so that it shifts the other bar. So when I say it shifts the other bar, so what we can say is that if we construct FBD of block m2, so if we consider FBD of block m2 in the x-axis direction, so the only force that is going to cause motion of 2 is spring force Kx, and the resistive force is frictional force. So the instant of time when Kx becomes equal to the frictional force, that is F2, then the second block will start sliding, and therefore we can say that Kx must be equal to mu m2g. So from here we can say that x equals mu m2g by k. So this is the value of spring force that is going to act on m2, and it must be greater than the frictional force to make it move. So this spring force is generated because of the displacement of m1. So if m1 is displaced by a distance x such that the system is displaced quasi-statically or slowly, and at this point the velocity is equal to 0. So what we can say regarding the points A, B and C is that some work is done by external force. So some work is done by external force, some work is done by frictional force, some work is done by spring force, and all of them together are contributing for the change in kinetic energy. So the force applied is constant, so a constant force F producing a displacement x will perform a work F into x. Frictional force is opposing, so mu m1g, and since block 2 haven't moved, so frictional force is opposing motion of block 1, mu m1g times x, since frictional force is opposite to the direction of displacement, work done is negative. And then spring force, so spring is opposing its elongation, so spring is having a work done of minus half kx square. And since there is no change in kinetic energy involved in the system till this instant of time, as the process is performed quasi-statically, so we are equating kinetic energy change to 0. Now from here we need to solve for F. So Fx can be written as mu m1 g x plus half kx square. So if we remove one x, so we are left with mu m1 g plus half k, and then one value of x can be substituted from here, mu m2 g by k. So k cancels out and we have the final answer. F equals mu g taken common, m1 plus m2 by 2. So for this problem, this is the correct answer that we have, that a horizontal force mu g m1 plus m2 by 2 be applied on the system consisting of the masses m1 and m2 connected by a spring which is initially in a non-deformed state, so that the shift occurs in the other bar.